in this first lecture, I will review some background from standard mechanism design theory and provide motivation for robust auction design. So, so a good place to begin is, of course, the famous paper by Meyerson. Okay, so here in this classic paper, we have, it's a very standard setting, n buyers and a single seller who is selling a single unit of the good. Okay, so, this is called IPV setting. So buyers have independent and private values. And then, this capital Fi is the CDF of the private value. The PDF, the density is the little f. Let's assume it is positive everywhere. And then the set of value is one-dimensional. It goes from 0 to some upper bound V bar. Okay, so we will write f without any index as the joint density of everyone's value. And then, following standard notation in game theory, we will write f minus I as the density of other people's value. Okay, so here for this auction game, the outcome consists of an allocation. We can think about allocations as a profile of probabilities. So they have to add up to something which is less than 1. Moreover, we have transfers. So how much money the bidders must pay to the seller. So the bidders or the agents, they have quasi-linear preference over the probabilities. And the transfer, so their utility is just VI times QI, how much the probability that they are receiving the good, minus TI, how much they have to give to the seller. And then the seller's utility, we will assume to be the total revenue, which is the summation across the transfer that he is receiving from every bidder. Okay, so this is and then just to review the basic setup, an auction has a allocation function. Oh, so first of all, it has let us call the message. Actually, let's call that the actions. Okay, so in general, mechanism has a set of actions that the players can take, and then it has allocation rule, so mapping from action profile to probabilities of allocation, as well as the transfer rule, which is a mapping from action profile to the how much they have to pay. Okay, so so this defines a game of simultaneous move. And then we will use the standard solution concept, which is Bayes-Nash equilibrium. Okay, so this is a standard definition. So just given the equilibrium strategy of the others, each player has no incentive to deviate from his or her equilibrium strategy. Okay, and a strategy is just a mapping from one's type or one's private value to a potentially a mixed action. Okay, so so in this framework, seller wants to maximize revenue by choosing some auction mechanism. Okay, so so basically we will look at, we will assume that players can walk away from the auction. So therefore, each auction must satisfy individual rationality constraints, IR constraints. So conditioning on every type VI, the expected payoff in equilibrium from this auction has to be weakly positive. And then and this is just a formula for the expected revenue in equilibrium at this auction. Okay, so we're interested in the optimal auction that maximizes the expected revenue in equilibrium. Okay, so here, right, as it is well known, we can simplify the auction design problem by focusing on direct mechanism in which the action space is exactly equal to the value space or the type space. And then we can just focus on truthful equilibrium in which every bidder of every type is just reporting truthfully his or her type. Okay, so the reason is that given any mechanism, given any equilibrium, we can construct a direct mechanism which just simulates this equilibrium. Okay, we just write the expected outcome from that equilibrium in this original mechanism, and then we will have a new mechanism, which is a direct mechanism. And the equilibrium in the new mechanism, M prime, is just the truthful equilibrium strategy. Okay, so here the important assumption is that seller can use direct mechanism without loss because the seller is choosing both the mechanism as well as the equilibrium. So that is a reason that the seller can combine these two objects, mechanism and equilibrium, into a single object, which is just a direct mechanism. Okay, so we can focus on direct mechanism because we are assuming seller is choosing the best equilibrium. Okay, and finally, the equilibrium condition in a direct mechanism, another, just to write it, is it's called the incentive compatibility condition, IC condition. Right, it just means that reporting your true value is an equilibrium. Okay, so for the IC condition, we need to we are looking at base Nash equilibrium. So what is important is the interim expected allocation. So let's write that as capital QI, and then the interim expected transfer, the capital TI. Okay, so type VI's interim expected payoff is just VI times QI minus TI. Okay, so so we just so the IC condition is just basically the optimal value to report is exactly VI. Okay, and here is a lemma which relates monotonic allocation function to incentive compatible mechanism. Okay, so this is a well-known lemma that a mechanism, a direct mechanism, is incentive compatible if and only if the allocation, interim expected allocation function is increasing with value, with reported value for every beta I. Okay, so the proof is very standard, right? So I have written the only if direction of this lemma here. So basically, we just take two types, VI and VI prime. Suppose VI is bigger than VI prime. Okay, so these two constraints, the first constraint is type VI doesn't want to pretend to be VI prime. And then the second constraint is that type VI prime doesn't want to pretend to be VI in this IC mechanism. Suppose we have a mechanism that's IC. Obviously, these two constraints have to be satisfied. Then we just add them together and then cancel out TI at VI and TI at VI prime. And then we get this equation, which obviously implies that the allocation received by the higher type VI must be bigger than the allocation received by the lower type VI prime. Okay, so this is the only if, and then the if direction just will come from the next slide. So, so here this is just writing this equation. We just write the IC condition. Okay, so this capital UI, the interim expected payoff for type VI, it is right. We maximize over WI the all possible misreporting of one's type. Right, so this mechanism is IC if we do not want to pretend to be someone else type. Okay, so notice that we are maximizing over WI. So by the standard envelope theorem, we can differentiate, when we differentiate UI with respect to VI, right? We can pretend as if we just differentiate this term. We can pretend that WI doesn't depend on VI. So, right, under some condition which is satisfied, the derivative of the expected payoff with respect to one's type is just one's interim allocation at the type, right? Just because here this payoff function, the partial derivative with respect to VI is just this term. Okay, so another way to write it is just saying that the payoff at VI is an integral of its derivative. So it's integral of capital QI from 0 to VI. Right, this is the fundamental theorem of calculus. And then this let us solve out the transfer because, right, we can use the definition of the payoff function, right? Payoff is value times allocation minus transfer. So we have, right, so we have a formula for the transfer. It's just the total surplus minus this integral, which is just expected payoff. Okay, and then we can, given this formula for the transfer function, then we can verify that if QI is monotone, then this the IC condition is satisfied. Okay, so right, so just substituting that. So first of all, the IR condition. Just saying that the expected payoff is weakly positive. Obviously, UI is increasing with one's type. So, right, this is for IR. We just need the lowest type having weakly positive payoff. Right. Obviously, to maximize revenue, we should set the payoff of the lowest type to be 0. Okay, and then substitute that envelope formula for the transfer here, and then apply Fubini's theorem. We get that the revenue is equal to the this term according to the allocation of that mechanism. Okay, so this term is called VI is called the virtual value. So the difference between the actual value VI and the virtual value is the inverse Haddon rate of the type distribution. So that is the informational rent collected by type VI from having the private information that his private value is VI. Okay, so in general, this is positive except at the highest type, where, of course, the CDF at the highest type is equal to 1. So this invert hazard rate becomes 0. Okay, so obviously, to maximize the equilibrium revenue here, right? So suppose this virtual value is increasing in VI for every bit of I, then clearly we can just do pointwise optimization. We should allocate the good to the bidder with the highest virtual value as long as it is positive. Okay, so this right. So in the regular case in which all of the virtual values is increasing, right? One optimal allocation is just right for bidders who have the highest virtual value and who have positive virtual value. We just randomize the allocation among such bidders. Okay, and then given the optimal allocation function here, we can work out the transfer function from the envelope formula. Okay, so notice that this allocation function is actually increasing ex post given any realization of others type. Okay, so this means that given the transfer function defined ex post for every profile of others type, given the transfer defined by the envelope formula, we will have this mechanism actually telling the truth in this mechanism is a dominant strategy because telling the truth is optimal whatever the type reported by the other bidders. Okay, and this mechanism, of course, can be implemented as a second price auction with a reserve price equal to the value at which the virtual value is exactly equal to 0. Okay, and another, right, this is not the only implementation. It can also be implemented as a first price auction with the same reserve price if we think about first price auction as an indirect mechanism. Okay, so this is everything is very standard. So actually now let me talk briefly about another perspective on the optimal revenue and on the optimal auction design in the Meyersen's framework. Okay, so suppose, right, so for technical reason, suppose let us discretize the space of value. Okay, so suppose the space of value is a grid separated by this by gamma, some small number gamma. Okay, so we have a discrete set of value. Okay, and suppose we want to solve the optimal auction design problem as a constraint optimization. So we can write down the Lagrangian. Okay, so this is the objective. Okay, so now suppose F is the probability mass function for this discrete set of values. Okay, so here we have the revenue, and then let us just look at local downward IC constraint. Okay, so for every value VI, we look at the IC constraint of not wanting to deviate to VI minus gamma. Okay, because VI minus gamma is just the next value immediately below VI in this discrete grid. Okay, so here this constraint must hold, right, taking expectation over others' value. So this constraint must be bigger than or equal to 0 because this is just saying that we do not want to deviate to, if we are VI, we do not want to deviate to VI minus gamma. Okay, so let's just put a multiplier in front of that constraint and combine it with the objective to have a standard formulation of a Lagrangian. Okay, and finally, when VI is equal to 0, right, where this constraint is just the IR constraint, the individual rationality constraint that reporting your type gives you weekly positive payoff. because we have an indicator function here. Okay, so here, right, suppose, so we are looking at a relaxed Lagrangian in which we look just at local downward IC constraint and IR constraint for the lowest type. Okay, so what is interesting about this partial relaxed Lagrangian is that, right, so Ti is a free variable. Okay, so its coefficient in this Lagrangian must be exactly 0. Otherwise, the seller can choose some Ti to make his Lagrangian and hence his revenue infinite. Okay, so the coefficient in front of every Ti at every value profile V must be 0. So this is so I have written out here the coefficient for Ti in this Lagrangian. So that coefficient must be 0. So this suggests that the optimal multiplier for the local IC constraint must be just the probability that that value is bigger than or equal to Vi. Okay, so here, so in this formulation, sometimes some people write here we have the interim probability, but sometimes people write the ex ante probability. So we just multiply F probability of type Vi. And then, and then we can also write, sometimes it's convenient also to write this constraint as a partial, as a discrete derivative. So divide by the grid size gamma. So if we do that, then in this optimal multiplier, we will just, just divide out these constant. So we will have a Vi, we will have the probability of this type, and then divided by gamma. Okay, so if we have these constant, of course, it doesn't matter for the incentive constraint because it must hold for every Vi. So these are just constant. But if we have these constant in the IC constraint, we will see that the multipliers is exactly the inverse hazard rate, right? Because the probability mass at the type Vi normalized by the grid size gamma is exactly the density, the analog of the PDF. Okay, so this will become, so this suggests that the optimal multiplier should be the inverse hazard rate for the value distribution. Okay, so this will be convenient in later lectures. Okay, and then we can just substitute, right? So the question is, are those the right multiplier? Are these, right, either without the normalization or with the normalization, are they the optimal Lagrange multiplier? So we can substitute these into the Lagrangian, right? By construction, all of the T terms drops out. Okay, and here, right, we basically have something like dq. Okay, so we can do a discrete integration by part to have actually, here we have d of alpha times Vi, alpha I times Vi. Okay, so we have this, this identity must hold, and then just substitute the value of, this value into the Lagrangian, we get the Lagrangian is exactly equal to the this analog, this discrete virtual value. So it's the expected virtual value in this discrete version according to the allocation in expectation. Okay, so this is exactly the optimal revenue from in the previous slide. Right, this is right. We have the value subtract the inverse hazard rate. Okay, so this suggests that the right multiplier is exactly the inverse hazard rate on the local IC constraint, and they suggest that the local IC constraint are actually the binding constraint. Okay. Okay, so far I have been talking about private value. So we can easily generalize this framework into interdependent value. Okay, so this is a model by Bulow and Klemper. Okay, so suppose now the value is a function of types, not only of beta i's type, but also everyone else type. Okay, so it's a function of Si and S minus I. Now the types are still independently distributed. Okay, so here, right, this is reasonable because we can think type as information possessed by each individual beta. So this just means that other people's information is important for my own value for this object. Okay, so in this setup, then we have a very straightforward generalization of the virtual value. So virtual value is the actual value subtract the inverse hazard rate times how sensitive my value is with respect to my type. Okay, so in the private value framework, value is exactly equal to the type. So this partial derivative is 1. Okay, so this, of course, this intuitively suggests that this is the right generalization of the virtual value. And we can also derive this virtual value using the same steps as in the previous slides. Okay, and then suppose we are looking at the regular case in which the virtual value is increasing with a type for every beta, then the same result as before will hold. The optimal allocation is to give the good to the beta with the highest virtual value as long as it is positive. Okay, so that's right. So here we have interdependent value, but still independent type. Then but the natural question is what happens when types are correlated? Okay, so that's the next paper that I will review. So this is basically Cremier and McLean. Okay, so for convenience, now let us work with finite discrete types Si. Okay, and then let us first, just for simplicity, look at the simple setting in which value is private. So one's value function only depends on one's type. Okay, and now, so we have correlated type. So this prior distribution for the type is correlated. Okay, which means that the interim belief about other people's type conditioning on my type, right here, I have different interim belief depending on the realization of my type Si. So we will have an independent distribution if this interim belief is exactly the same for every realization of Si. Okay, so now we allow for correlation. And then, the previous formulation carried over very straightforwardly here. Okay, so revelation principle continue to hold because we are, because the seller is picking both the mechanism as well as the equilibrium. Okay, so we can choose the action space of the mechanism to be exactly the type space. And then, so now this is the new condition for the IC condition, So for IC condition, we are, we just take expectation over other people's type according to our interim belief function, conditioning on our type. Okay, so IC condition just says that we do not have an incentive to lie and misreport our type to be Si prime. Okay, and then this is an analog of the individual rationality condition, So given our type Si, if we report Si to the mechanism, our expected payoff is weakly positive. Okay, so now let us define a revenue benchmark, which is the total surplus. Okay, so total surplus, right, for every realization of the type, the maximum efficient surplus is just the highest value among all of the bidders. Okay, so suppose for every realization of the type profile, we just take the maximum value, okay, and then we just take expectation of that, so we will call that the total surplus. So clearly the total surplus is an upper bound on the revenue that any seller can achieve in equilibrium, okay? And then the basic, right, the surprising conclusion of Cremier and McLean is that this total surplus is actually achievable. Okay, so there actually exists IC and IR mechanism such that the revenue is exactly equal to the total surplus. Okay, so how they are doing this is through the following basic strategy. So first of all, we just start with a auction mechanism which is ex-post efficient, okay, which allocate the good efficiently. Okay, so if we just use, for example, like a second price auction, the bidders will have information rent, so they will have a positive expected payoff. And then we can extract those positive expected payoff with side bet by leveraging the correlation in their belief. Okay, so here is the detail of how we can achieve full surplus extraction through side bet. Okay, so let us suppose that for every bidder and every type, the interim belief at the type Si does not lie in the positive linear span generated by the interim belief of other type. Okay, so there does not exist weight row at which we can write interim belief conditioning on Si as a positive weight over the other type's interim belief. Okay, so for every bidder I and every type realization Si, this is not possible. Okay, so that is the condition. So this is basically saying that there is enough linear independency in the interim belief across type for every bidder. Okay, so given enough linear independency, there exists IC and IR mechanism whose revenue is exactly equal to the total surplus. Okay, so here, right, so let me briefly go through the proof. The proof is quite simple. So here we basically, right, we have two steps. The first step is let us achieve ex-post efficient allocation. So let us allocate the good to the bidder with the highest value. Okay, so let the allocation to be the ex-post efficient allocation. And then the idea is to construct the transfer so that IC condition is satisfied and IR conditions are binding for every bidder and for every type. Okay, so right, so this assumption that the interim belief does not lie in the positive span or in the convex cone generated in the interim belief of other types will imply that, right, by the Farkas lemma, there exists separating hyperplane GI for every type Si. Okay, so this vector is we think of that as in the vector space over S minus I. Okay, so for every type profile of the other player, we will have some number Gi, which we will use to construct our transfer. Okay, so right by the Farkas lemma, by our hypothesis, we can, there exists separating hyperplane such that this Gi is exactly orthogonal to the integral belief at type Si, right? This Gi at type Si is exactly orthogonal to the belief at this type. Okay, so they are exactly targeted for the belief, and then moreover, the dot product between Gi at Si and belief at Si prime is exactly positive. Okay, so clearly this is not possible, right? If pi viewed as a vector at type Si is in the positive span across pi at Si prime, right? Because we have positive dot product. So if we can write this pi as a positive combination of pi at Si prime, then clearly we cannot have 0 here. Okay, so Farkas lemma tells us that the converse is also true. If they are not in the positive span, then in fact we can have this kind of separation in terms of the hyperplane. Okay, so this is very useful because our transfer is just the surplus generated by the exposed efficient allocation plus some side bet, which is exactly this Gi, right, constructed, targeted for each type Si, multiplied by some large weight gamma to amplify the effect of the side bet. Okay, so this is nice because right by our construction, the expected transfer from telling the truth, right? Suppose my type is Si. If I tell the truth, then I pay exactly my surplus from the efficient allocation, right? Because just using the fact that the dot product of Gi and my belief at my type Si is exactly 0. Okay, so on average, I will pay exactly my surplus from the allocation. So my expected payoff is 0, whatever my type is. Okay, so therefore the individual rationality constraint is satisfied. In fact, it is binding. Okay, so but what if I misrepresent my type to be Si prime? Okay, so right then, according to the transfer definition of the transfer, this is my expected payment through the expected transfer. So I pay the expected allocation. Suppose I misreport, claiming my type is Si prime. This is right. This is in general positive. And then right, I have to pay according to this Gi. But according to my misreport, Si prime, and remember, that is right, this dot product is positive. Okay, and kappa is a big number, so this part is going to be huge. And we will choose kappa so that this term, the side bet, dominates any benefit I can get through misreporting in this part. So of course, when kappa is sufficiently big, according to the construction of Gi, I have no incentive to misreport. So IC condition is satisfied. So in equilibrium, I will generate this much payment to the seller, and that is exactly full surplus extraction. Okay, so here with correlated signal, right? So now let's look at so one natural setting in which we will have correlated signal is in fact we have correlated volume. So suppose right. So let us look at this example of a common value setting. So suppose all buyers have the same exposed value. Okay, so let us depart from the previous private value assumption. So one very natural possibility is that conditioning on the value, all of the bidders receive IID signals as I. Okay, so this is a mineral rights model, right? So the common value is sort of the state of the nature. Either there's lots of oil here or there's very little oil, and all of the bidders have independent assessment. So their signal will be independent, conditioning on the state of the world. Okay, so because the value or the state of the world is not observed, even though these signals are independent, conditionally independent, but ex ante they will be correlated. Okay, so therefore it is right in terms of the interdependent valuation function, we have VI. It depends on the realization of everyone's signal or type, which is just the conditional expectation given the type profile. Okay, so here it is a common value model because this function VI is the same for every bidder. Okay, so this is a natural setting where we will have correlated signal. So in fact, we can adopt the previous argument easily to this setting because here it's even simpler, right? Because any allocation function that always fully allocates the good is expose efficient. So we can use any allocation function as long as it just fully allocates the good with probability 1. Okay, and then, so we start from that as a benchmark, and then we construct the side bets as before, because remember in the side bet, in those function GI, that just depends on the ex ante correlation in the signal. Okay, so the same proof works exactly, and then we will have a full surplus extraction of the common value. Okay, so this works if we have assumed that to apply Farkas lemma that the set of signals is finite, and then there are also generalization of the full surplus extraction when signals are infinite. Okay, so this is so the full surplus extraction is a very powerful result, but it is certainly counterintuitive, and it's not something that we observe in practice. Okay, so there are various critiques on this result, on the full surplus extraction result. So first of all, if these interim beliefs are close to singular, so if the distribution of the types are close to being independently distributed, then the side bets will have to be enormous. So to have those separating hyperplane, because these interim beliefs will be very close to each other, as we vary the type. So we have to really make those GI to be enormous to leverage the small difference in these interim beliefs if pi is close to independent. So, so this means that we have to use very large transfer after signal realization, which is obviously problematic if there are limited liability in terms of what people are can pay, or if the bidders are risk averse. Okay, so that's one problem with full surplus extraction. A related problem is that to construct those side bets, we have to have exact knowledge of those beliefs of the prior distribution or equivalently of these interim beliefs. Okay, so which means that, right, if these beliefs are misspecified, it can have very serious implication for the bias, because by construction, if we get the belief exactly right, the bias are just breaking even. So if we get them wrong, we could go causing the bias to go bankrupt, losing millions of dollars on average, which is obviously problematic for the bidders. Okay, so for these reasons, right, so the implausibility of the full surplus extraction motivates work on robust auction design. Okay, so the idea of robust auction is right, to have an auction which is guaranteed to work well regardless of the distribution of belief, regardless of who knows what about the value. We want to have some sense of guarantee that the auction can work well. Okay, so that naturally that leads to the next lecture that Ben will